lecture. All right. Chapter 13 is about complex numbers, and then we talk about analytic functions later on, and develop some theories to get into residue theorem and residue integration, and that is useful for not only learning about complex numbers in a lot of depth, but also to perform some integrations that are hard to do with real analysis. So that is the goal. So 13, 14, 15, 16 are about complex numbers. All right. So what are complex numbers? To begin, we just introduce complex numbers as a number z, which is complex, which is x plus iy. X and y are real, and I has this property that we call it imaginary number, whose square is -1. So you know there's no real number whose square is negative, but I has this property. So this is the defining property of I, or you can say I is square root of -1, which doesn't exist in real numbers. And this x that is real is called real part because it doesn't have imaginary number beside it. And the y without the I is called the imaginary part of z. We have these notations. We say x is real of z, means real part of z, and y is imaginary part of z, im of z. So these are basic definition of real complex number, which is z, real part, imaginary part, and what is this I squared is -1. And because you see this, there is real part, imaginary part, so basically each z is identified by two real numbers. It is a point, it is like a point in XY coordinate system. And so in order to show a point, we needed two axes, one real axis we call it, that shows x, and y axis that shows imaginary part, imaginary axis. And every complex number that has a real part and imaginary part is a point basically in this complex plane. We call it complex plane. So it is like a point in two-dimensional coordinate system. And this is, for example, if you say what is 4 minus 3i, means that it has the x coordinate of 4 and y coordinates of -3. And I itself is right here because it has no real part and imaginary part is 1. All right, any questions so far? Is it clear? All right, this is complex number. And then how do we add or subtract two complex numbers? The way we add or subtract is like exactly like vectors, a vector from origin to that point. And or we can just write these two like two binomials, z1 plus z2. Z1 is this, x1 plus iy1, and z2 is x2 plus iy2. And if you add them, you can just add all the terms, but collect similar terms, means that x1 and x2 are the real parts, so it becomes x1 plus x2. And the imaginary parts you can add by and factor the I, so it becomes x1 plus x2 plus I times y1 plus y2. And as you see, it is like vectors. You see, if you add these two, z1 and z2, like two vectors, the result will be the vector sum of these two, because you see that x, or the real part of the sum, is the sum of the real parts, and the imaginary part of the sum is sum of the imaginary parts of the two numbers. So it's the same as vectors, where you find the x component of the sum is sum of the x components, and the y components of the sum, y component of the sum is sum of the y components, right? So it's exactly like a vector. And even if you subtract two vectors, two complex numbers, it is the same as subtraction of two vectors, because you get x1 minus x2 and then y1 minus y2 as the imaginary part. And this is the way z1 minus z2 is. So you can add negative z2 to z1. So it comes like this. So this is z2, this is negative z2. It's like z1 plus negative z2 becomes this z1 minus z2. So it works like vectors, but we cannot multiply vectors by each other directly. We have, of course, for vectors, we have cross product and dot product, but here we have multiplication of two complex numbers and also division of two complex numbers. And in vectors, you remember that we don't have any definitions for division of vectors, but here we do. So how do you multiply? Multiplication of two complex numbers is like multiplication of two binomials, and then you multiply these two, but whenever you have I squared, you replace it by -1. So this becomes x1, x2. In fact, you FOIL this, x1 times x2 times x1 plus x1 times I y2, so becomes I x1 y2, and then becomes I y1 x2, and then becomes I times I squared y1 y2, and I squared is -1. So you replace that by -1. So this multiplication becomes x1 x2 minus y1 y2, because this becomes a -1. So this is the real part, and you factor I from these, you get imaginary part. So x1 y2 plus y1 x2. All right, so this is the multiplication, basically multiplying the binomials, and whenever you get I squared, you just replace it by -1. And now we have a definition of complex conjugate. What is the complex conjugate of a complex number? By definition, a complex number z, which is x plus iy, has a complex conjugate. We denote it by z bar, and it is defined as x minus iy. It means that basically flipping the sign of I, or flipping the sign of the imaginary part. All right, so this is complex conjugate of z, which is x plus iy. That is general definition. And if you look at the in the figure or in complex plane, graphically, you see that the imaginary part flips over. The real part stays the same. For example, 5 plus 2i is this point. It has a real part of 5 and imaginary part of 2. And if you do the complex conjugate of that, it becomes 5 minus 2i. So the real part stays the same, but the imaginary part flips over. So it is like a reflection around the real axis, right? So the complex conjugate of a number is a reflection of that number around the x-axis. And of course, as you see, if a number is already real, then its complex conjugate is the same as itself. Or if a number is purely imaginary, means that it doesn't have a real part, then its complex conjugate is negative of itself. So note that if you multiply a number by its complex conjugate, you see it becomes x squared minus ixy, and then you get plus ixy. They cancel each other, and then you get I times negative I becomes 1 times y squared. So if you multiply these two, it becomes x squared plus y squared, and it is a real number. So if you multiply any complex number by its complex conjugate, you get a real number. That is the sum of the squares of real and imaginary parts of that number. And we call the absolute value or modulus of the complex number z as the square root of this multiplication, the square root of z bar, or square root of x squared plus y squared. As you see, if x is the real part and y is the imaginary part, this will be the distance of that complex number to the origin, which is 0. Okay, that is called the absolute value of a complex number, or modulus of the complex number. So this complex conjugate, which is defined like that, is helpful in just summarizing what this modulus is. It's just square root of z bar. Complex conjugate has these properties, and it is very easy to show that if you want the real part of the z, you can add z to z bar. You see, if you add z and z bar, the complex or imaginary parts cancel each other, and you get twice the real part. And if you divide by 2, you get the real part. And if you want to get the imaginary part, you can subtract z and z bar. So z minus z bar becomes twice the imaginary part. And if you divide by 2, I cancels, and you get the imaginary part, which is real. You see, both real part and imaginary parts are real numbers. Doesn't include the I, okay? And any questions so far? You can also show very easily that the complex conjugate of sum of two complex number is sum of the complex conjugates. And the complex conjugate of the difference is the difference of the complex conjugates. The same for multiplication. The complex conjugate of z1, z2 is z1 bar and times z2 bar. And the complex conjugate of division of two complex numbers is the division of the complex conjugates, right? So these are the properties of complex conjugate. It is easy to verify, and I'm not showing how. You can show it by yourself. If you have trouble, you can come back to me and I will show you. All right. Any questions so far? All right. Now, how do you divide two complex numbers? The division of two complex numbers also works like a division of binomials. But then multiply both numerator and denominator by the complex conjugate of the denominator, and simplifying so that we have a real number in the denominator. So basically, if you divide, you don't want, usually you don't want the I or complex number in the denominator. So you multiply both numerator and denominator with the complex conjugate of the denominator, and then the denominator becomes real. And then you can sort it out like this. See, if you want the z1 divided by z2, it is x1 plus iy1 divided by x2 plus iy2. And now you can multiply both numerator and denominator by the complex conjugate of this, which is x2 minus iy2. So you multiply by x2 minus iy2 and multiply. So you multiply and divide by this, which doesn't change the fraction. And then the denominator becomes x2 squared plus y2 squared, becomes real. So you get this. In the numerator, you get x1, x2, and plus y1, y2 as the real part, divide by the denominator, which is the real number, plus the imaginary part will be x1, y2 with negative I, and y1, x2 with positive I. So y1, x2 minus x1, y2, like that, divide by this. So basically it becomes this plus I times that, divide by this number, and we can separate the two parts. So the division of Z1 and Z2, Z1 over Z2 has a real part given like by this and imaginary part given by this. All right. Does it make sense? Any questions? All right. Here is some practice. I want to show you just how to add or subtract number. So I'm going to write here on the board. So Z1 plus Z2, if Z1 is this and Z2 is this, what is Z1 plus Z2? Very easy. You add the real parts, then we write 8 plus 3i plus 9 minus 2i. And then you add the real parts, 8 plus 9 as the real part, and plus I times 3 minus 2, right? So it becomes 17 plus I, or 1I. When it is 1, we don't write the 1 as in algebra. So 17 plus I will be sum of these two. What is the difference of the two? Becomes 8 minus 9 as the real part, and 3 minus negative 2 plus I times 3 minus negative 2. So it becomes negative 1, and this becomes 5 plus 5i. You know what happens sometimes. This doesn't work. And so this is the subtraction. What is the multiplication? It's a 8 plus 3i times 9 minus 2i becomes 8 times 9. How much is 8 times 9? 72. I don't know what's wrong with. See, I want to write up there, it writes something down here. Yeah. So 8 times 9, 72. Yeah. So then you have negative 16i, and then you have 27. I, and you have I times I negative. With this negative becomes positive. 3 times 2 is 6, right? Negative 6i squared becomes plus 6. So 72 plus 6 is 78 as the real part. There's something wrong with the laptop or
Is your pen dying? Is your pen, the battery dying?
I don't know. There's a battery in it. Yes, I maybe.
I'm not sure. It depends on which pen you have.
Yeah, probably there's a battery. So, but you know, I'm writing somewhere here, something here. It writes something here. I don't know why. It's not a battery problem. I don't think it's a malfunction. Anyhow, you see, 72 and 7 and 6 is 78, as some of you already calculated. 27 minus 16 will be 11i. All right. So this will be the multiplication. And if you want to do the division, we do Z1 over Z2, 8 plus 3i over 9 minus 2i. Multiply both numerator by and denominator by 9 plus 2i. Oh God. I don't know why.
You're not touching the mouse pad while you write, are you? On accident?
No, I have a glove. This the way I always do. I have gloves so that it doesn't touch anything, but maybe it does sometimes. So multiply by 9 plus 2i, 9 plus 2i. So in the denominator, we get 9 squared, which is 81, plus 2 squared, which is 85. In the numerator, we have the 8 times 9, 72. And then you have minus 3 times 2, 6, plus I times, I can't get rid of these now. 8 times 2 is 16, plus 3 times 9, 27. So that becomes 66, right? Plus 5 times 16.27 will be what? 30, 23, 43. I think maybe I'm touching something down here. Divide by 85. So it becomes 66 over 85 plus 43 over 85. All right, this is the division. Any questions? All right, so yeah. Oh, there's something wrong here. It doesn't work at all. In my PowerPoint, there's some glitch or something. Yeah. All right. So let me. All right. All right. No worries. Let's continue. Yeah, it will take a while if I want to restart the computer, but let's see if we can continue. If it happens again, then I'll do something. So here is the basically A plus BI. If Z1 is A plus BI in general, Z2 C plus DI, we want to verify these things that we said. So you can do some for yourselves. I may do this part C, as an example. So what is Z1, Z2 bar? We have, let's do this one. Z1, Z2 bar. What is that? Means the complex conjugate of this Z1, Z2. Z1, Z2 will be AC minus BD. This is the real part, right? And the imaginary part is AD plus BC. AD plus BC. And the complex conjugate, this bar means AC minus BD minus I times AD plus BC. This is the complex conjugate of that. On the other hand, if you multiply Z1 bar times Z2 bar, see what we have. In this case, you have A minus BI times A it's frustrating. And then Z2 bar is C minus DI, right? And then if you multiply these two, you get AC minus BD, because it's minus and minus, and then I times I becomes negative BD. And then the I part becomes negative AD, I, and then negative BC I. And then if you factor the negative sign here, if you factor the negative sign, it becomes AC minus BD as the real part minus AD plus BC, which is exactly what you have here, right? So these two are the same, means that actually verified that the two sides of this equation are the same. And you can do the same for the other one, especially this one. You can verify by yourself, right? Another thing that can show is that the identities that we have for real numbers, they actually work for complex numbers. Like this Z1 plus Z2 times Z1 minus Z2 is equal to Z1 squared minus Z2 squared. You can verify that by, actually you can verify in general if you take Z1 as A plus B I and Z2 as C plus DI. If you do that, you can generally show that these two are always the same. But here is an example. We want to find these two. So we found Z1 plus Z2, which was 17 plus I. That was Z1 plus Z2. And Z1 minus Z2 was negative 1 plus 5I. Right? And then if you multiply these two, you get negative 17 and negative 5, and then plus I times, you have a negative 1 and 17 times 5. What is the 17 times 5 is 85, right? So that's 85. Yeah, I think when I touched the screen, something happened. 85 minus 1 times I. So this becomes negative 22 plus 84I. And then if you do it this way, Z1 squared, so Z1 squared becomes 8 squared minus 3 squared, right? And plus I times 2 times 8 times 3, right? 6 times 8, 48. Right? This is Z1 squared minus Z2 squared. Z2 squared will be 9 squared, 81, minus 2 squared, minus 4, and then plus I times 2 times 2 times 9. So 2 times 18 is 36. So becomes negative 86, 36i. So if you subtract, you get 88 squared minus 3 squared is 64 minus 9 will be 55. 55 minus 81 is the imaginary real part, plus I times 48 plus 36. So 55 minus 81 is 22, is that? No. Did I do it right? This is 64.
64 minus 9 is, oh yeah, 55. Yep.
You forgot to
64
subtract the
minus
4.
55. And then, oh, this is not 81. 81 minus 4. 81 minus 4 is 77. So 55 minus 77 is negative 22, and 48 plus 36 is 84, isn't it? Plus 84. So you see that you get the same thing in either case. 48 times 36, which is 50 plus 34. Yeah. All right. So you can play around. It is important for you guys to just work arithmetic with complex numbers so that you become fluent in that. You become comfortable with that, because this is quite different from what you have in real life. All right. Any questions? All right. Here we want to show for z equal to x plus iy. In terms of x plus x and y, find imaginary part of 1 over z. For example, what is imaginary part of 1 over z? So 1 over z is this, is 1 over x plus iy. You can multiply by x minus iy and x minus iy, and becomes, the denominator becomes x squared plus y squared, and the numerator is x minus y. So you can write this as x divided by x squared plus y squared minus I times y over x squared plus y squared. So the imaginary part of 1 over z is this number, that the factor of negative I, not the I. So becomes negative y divided by x squared plus y squared. Things like that. You can verify the other ones by yourself. And here, I think I have it like that. Imaginary of that becomes negative y divided by x squared plus y squared. If you do z over z bar, you get that, and then you multiply both numerator and denominator by x plus iy. So it becomes like this. So it becomes x plus iy squared, basically. X squared minus y squared plus 2ixy. And so the imaginary part is the coefficient of I, which is 2xy divided by x squared plus y squared. And then 1 over z squared becomes this, 1 over x squared minus y squared plus 2ixy. And then you can multiply both numerator and denominator by the complex conjugate of the denominator. Then you get this squared plus 2xy squared. It becomes 4x squared y squared. That's the denominator. The numerator is the complex conjugate of the denominator. So it becomes like that. So you see that the imaginary part is the coefficient of I, which is all of this, right? So it becomes negative 2xy divided by x squared minus y squared quantity squared plus 4x squared y squared. You can, if you write this out, you can show that it is like x squared plus y squared as it should be. You see, this becomes x squared. This part becomes x squared plus y squared minus 4x squared, sorry, x to the 4th becomes x to the 4th plus y to the 4th minus 4x squared y squared plus 4x squared y squared minus 2 x squared y squared plus 4x squared plus y squared becomes x to the 4th plus y to the 4th plus 2x squared y squared, which becomes x squared plus y squared. Okay. So the denominator becomes x squared plus y squared, and then the factor of I becomes negative 2xy divided by the denominator. So negative 2xy divided by x squared plus y squared. All right. Any questions? Pretty simple calculations. You just need to get familiar with how to do arithmetic with complex numbers. All right. What is the polar form of complex number? The same as polar form of vectors. You see, you can denote this point, which is a complex number, by its real and imaginary part, which is x and y, x and y, or you can denote it by how far it is from this origin, which is r, you call it, or absolute value of z, or modulus of z, and at what direction is it from the real axis, counterclockwise. So you can denote these complex number in two different ways, and these two are related. For any value of x and r and theta, x is always the r, which is the modulus, times cosine of theta, as you see in this right triangle, and y is r sine theta. So we have x equal to r cosine theta and y equal to r sine theta. This comes from basic math. But of course, theta can be any value, and it always gives you the right value for x and y. And the z can be written as r cosine theta as its real part, and r sine theta as imaginary part. And r is usually factored. So you get r times cosine theta plus I sine theta. All right? This is the polar form of the complex number x plus I1. And the absolute value or modulus is r, which is square root of x squared plus y squared, or square root of z bar, as we said before. And theta, if you want to find theta, you see that in this right triangle, theta is opposite over adjacent, which is y over x. So theta will be tan of theta. So tan of theta is opposite over adjacent, but therefore theta is tan inverse of y over x. But this is not quite complete because it never gives you anything theta in this in the second or third quadrant. It only gives you in the first quadrant and fourth quadrant. All right, because tan inverse only has values between negative 90 degrees to 90 degrees, or negative pi over 2 to pi over 2. right? So if a z, a complex number, is in here, or if it is in the third quarter, if you calculate that, tan inverse of y over x, for this one, it gives you this number. For this one, it gives you this direction. So in order to fix that, you need to add 180 degrees or pi to the tan inverse of y over x to get to the right direction. All right? And okay, when do we do that? When do we do that? In vectors, we mentioned that if the x component is negative, then you add 180 degrees or pi to the value of tan inverse of y over x. In here also, if the real part is negative, means that you are in the second or third quadrant. In that case, you add pi to tan inverse of y over x, and you get to the same, the right direction, or the right angle. All right. So we add pi if x is negative. All right. And of course, if x is 0, you are in the imaginary axis, and the angle is either 90 degrees or negative 90, or either pi over 2 or negative pi over 2. That's clear. But if x is not 0, you can find tan inverse of y over x. And if x is negative, you add pi. This always gives you the exact direction of the complex number with respect to the origin. And that number, that theta, is called the argument of the complex number. So we have modulus of the complex number and the argument of the complex number. And also, if you add a multiple of 2 pi, which is 2k pi, k is integer, you can add any multiple of 2 pi to the angle, and it doesn't change the complex number. So you can always add these 2k pi to the argument. And you add pi to tan inverse of y over x if x is negative. All right, is that clear? All right. So this theta is called the argument, the angle theta is measured in radians from positive x direction counterclockwise. And this theta, if it is between negative pi and pi, we denote that by capital ARG of z, means argument of z. And in any other case, when you have multiple of 2 pi added to it, it is sometimes we have 0 to 2 pi. If the multiple is added to it, multiple of 2 pi z, 2 pi multiple of 2 pi to the angle, we call it a argument of z with lowercase a. So in general, we have lowercase argument of z, but when we say capital R z, means that it is in the first term of the circle, which is sometimes it is depending on the book. Some books say from negative pi to pi. Some books go from 0 to 2 pi. Call it the first round. It depends on the book. All right. So both ways for us is okay. Any questions? So in polar coordinates, we have argument and modulus, which is r and theta. And in Cartesian coordinate, Cartesian form, we have x and y. And they are related, as you see here. If you have r and theta, you want to find x and y, you use these two equations. If you know x and y, you want to find the argument, you use these two equations. Right?
So Professor,
ways. Yes, please.
yeah, when do we need to add a 2k pi?
You, in general, if you want to show the angle, what is the angle in general, you need to add 2k pi, because if you add 2k pi, it is the same complex number, right? So general value of theta has this 2k pi. Okay.
Okay, thank you.
So that is the polar form of complex numbers. And then you see what happens if we multiply two numbers in polar forms. So if you have a complex number, two complex numbers in polar forms, like Z1 and Z2, the first one has a modulus or absolute value R1, and it makes an angle theta 1 to the x-axis or to the real axis. The second one has a module R2, and it makes an angle of theta 2. So if we multiply these two, this is what we get. See, first R1 times R2, and then we have cosine theta 1, cosine theta 2. Let's write these first. So we have cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2, right? This is the real part. The imaginary part will be sine theta 1, cosine theta 2 plus cosine theta 1, sine theta 2. Do these expressions sound familiar? Do you remember these from trig? These two? If you remember, this is the formula for cosine of theta 1 plus theta 2. And this is the formula for sine of theta 1 plus theta 2. So you can write Z1, Z2 as R1, R2 times cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. This is hugely interesting because it says in polar coordinates, if you multiply two numbers, the absolute values multiply, so you get a number whose distance to the origin is the multiplication of those two distances, and then you get an angle that is sum of the two angles. Isn't it interesting? So this is very important. So what this implies is that probably we can denote Z1 and Z2 as this, as exponential form. For example, Z1 is R1 times E to the I theta, and Z2 is R2 times E to I theta 1, and R2 E to the I theta 2. Because if you multiply these two, Z1, Z2, right, becomes R1, R2, R1, R2 times E to the I theta 1 plus I theta 2. The powers add, right? And then becomes R1, R2, E to the I theta 1 plus theta 2. So you see this property follows if you have this exponential form. Therefore, there's an exponential form of complex numbers. So exponential form is, as I said, this R e to the I theta. Because you see, if you write it in terms of exponential, it carries this property that's multiplication of two numbers is a number that has the multiplication of modules or multiplication of absolute values, and then the angles add. So, and then you look at this, it's a polar form and exponential form. R cancels there, and then you see cosine of theta plus I sine theta is e to the I theta. And this is Euler's formula, which is very important in complex numbers. All right? Any questions? So we have Euler's formula. There is another way I can show you this Euler formula is a correct formula by if we extend the Taylor series to the complex numbers, which we don't have a proof yet, but assume that Taylor series can work for complex numbers, then we can expand e to the I theta in terms of Taylor expansion, in terms of like e to the x. Remember e to the x, but before we do that, sorry, we should look at what are the powers of I, because if we do Taylor expansion, we encounter powers of I, and you see that I squared is -1. What is I to the power 3? I to the third power?
Negative I.
Negative I. What is I to the fourth power?
Positive 1.
Positive 1. What is I to the fifth power? You get again I. So you see it becomes I -1, negative I 1, and I -1. It rotates between all of these because every time it rotates 90 degrees. See, if you multiply I by I, you get -1. That's I rotated by 90 degrees, which is what we just found out. And then you rotate another 90 degrees, you go to negative I. You rotate another 90 degrees, you get to 1, right? So this is that basically, this is I. It has 90-degree angle to the x-axis. If you square it, the angle doubles, so you get to -1. If you multiply by another I, it goes to this point, and then another goes to this point, and then rotates again and again between these 4 points. So in general, I to the 2n becomes I squared to the n power. I squared is -1, so I to the 2n becomes -1 to the n. And what is I to the 2n plus 1 becomes this -1 to the n times I. So I to the 2n plus 1 becomes -1 to the n power times I. All right, so these are all powers of I. If you raise I to this even power, it becomes a real number, either 1 or -1. If you raise it to an odd power, it becomes that -1 to the n times I, so it becomes imaginary number, either I or -I. All right. So now let's assume that we can use the Taylor expansion of e to the x for e to the I theta. So if we have e to the I theta, we can write it as sum over k from 0 to infinity of I theta to the power k divided by k factorial. Remember, the e to the x is sum of x to the k divided by k factorial. That's the Taylor expansion for e to the I theta. And then this numerator become I to the power k times theta to the power k divided by k factorial. And then we can separate the odds and evens. For the even powers, I theta to the power 2n divided by 2n factorial, I to the power 2n becomes, I will say, these are the odd, even powers. These are the odd powers. So I separated the even powers and odd powers. But I to the power 2n in the first summation becomes -1 to the power n. I to the power 2n plus 1 becomes -1 to the n times I. So all of these in the second one have an I. All of these are real. So we can factor this I from the second one and write it like this, and the first one like this is real. The second one, we can factor the I and write it like this. All right. And now Are these familiar to you? This series from calculus?
The Taylor series.
Yeah, this one and this one
Yeah.
are should be familiar. The first one is cosine theta. Remember, it has all the even powers. The second one is sine theta. So this is cosine theta plus I sine theta. Again, you see that e to the I theta is cosine theta plus I sine theta. All right. Any questions?
So this is the other way to get Euler's equation, right?
Yes, Euler's formula. Yes, you can see that through the Taylor expansion as well. That's the purpose of this part. All right. Any questions? All right. I know I'm going a bit too fast, but you know, it's a quick review of complex numbers, and we're going to do that pretty fast to get into analytic functions and all of that. So this is Euler's formula, which is one of the very interesting formulas in mathematics. All right. All right. So how do we define inverse of a complex number? Of course, we already did that in coordinate in the Cartesian form, how to do 1 over z, but we want to do that in polar form. Suppose z1 and z2 are the inverse of each other. And then if you do z1 times z2, we know that it becomes like that from this formula above here. And then if they are inverse of each other, it becomes equal to 1. So z1 times z2 equals 1. And 1 can be written this way, like a module of 1 and argument of 0. Means r is 1 and theta is 0. You see in the complex plane, 1 is like this, like in this point, x and y. Real and imaginary. 1 is here. So you can, in polar form, you can say that it has a module of 1 and it has an angle to the x-axis of 0. So you can write it as 1 cosine 0 plus I sine 0. You see cosine 0 is 1, sine 0 is 0, so it gives you 1. But then you need to compare these two together and say that, okay, if this complex number is equal to that complex number, then R1, R2 should be 1. Right? The modules should be the same and the angles should be the same, right? So R1, R2 is 1. So R2 is 1 over R1 and theta 1 plus theta 2 is 0. Therefore, theta 2 is equal to negative theta 1. So the inverse of a complex number can be found by inversing the argument, inversing the module or the absolute value and making the angle negative. Cosine of negative theta and sine of negative theta. Of course, cosine of negative theta and cosine of theta are the same. Sine of negative theta is negative sine theta. So we can write it R inverse cosine theta minus I sine theta. And again, if you look at it in exponential form, this has negative theta as a number, so it becomes R inverse times e to the negative I theta, which is the same as looking at, you see, R e to the I theta, and then raise it to the power negative 1, as you know, it becomes R inverse times e to the power negative I theta, right? So it works like that, follows the property of powers and multiplication in powers and power over power. So it is e to the I theta to the power negative 1. You multiply the powers, right? It becomes e to the negative 1 times I theta, right? So you see that it works, everything works perfectly like that. So the division of Z1 over Z2 becomes R1 over R2, and cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Or in exponential form becomes R1 over R2 e to the power I times theta 1 minus theta 2. All right? So when you multiply, R's multiply, and then theta's add. If you divide, R's divide, and theta subtract. All right? Do you see the pattern? So everything perfectly fits together. We can have the complex numbers in polar form, or you can have it in exponential form. And everything follows the algebra that we previously know. So all the algebra that we have for real numbers comes to complex numbers, and everything works perfectly. All right. Any questions here? Okay. So now we want to investigate integer powers of a complex number. What is the, if you have z equal to r cosine theta plus I sine theta, which is the polar form of z, now we want to raise it to the nth power. Z to the n becomes r to the n, and then the angle becomes n times what it was. So cosine of n theta plus I sine n theta. So that is obvious, right? Because the multiplying by itself, the theta becomes 2 theta, 3 theta, and until n theta, and r raises to the power n. All right, this is pretty simple and very fast to get to. But the interesting thing that this gives us is the following. We have a de Moivre formula that says that cosine theta plus I sine theta to the power n becomes cosine of n theta plus I sine n theta. See, this is r to the n, and this to the n if you raise everything to the power n. So if z to the n is written both ways, therefore this must be equal to this, which is the case. And so this is an interesting formula. Not only it is interesting, but also it is very useful in finding the sine and cosines of multiples of theta. For example, if you use n equal to 2, cosine theta plus I sine theta squared, you can square that and write cosine squared theta minus sine squared theta plus 2I sine theta cosine theta, right? On the other hand, you can write this as cosine of 2 theta plus I sine 2 theta, right? And then if these two numbers are the same, then the real parts and imaginary parts should be the same. So cosine of 2 theta becomes cosine squared theta minus sine squared theta, and sine of 2 theta becomes 2 sine theta cosine theta that we know from before. And you can do that for the third power. And if you write in third power, you see it becomes the second power that we have up there times this one, cosine theta plus I sine theta. And if you do the math, you get cosine cube theta minus 3 cosine theta sine squared theta as the real part, because you see the real part becomes this times that minus this times this, and then it sums up to cosine cube theta minus 3 cosine theta sine squared theta, and then the imaginary part you can calculate and get 3 sine theta cosine squared theta minus sine cube theta. And because this again is equal to cosine of 3 theta plus I sine 3 theta then this should be equal to that, and sine 3 theta should be equal to that, which are two identities that we know from 3. So we can derive those 3 identities here. All right. So we find cosine of 3 theta, and the same for the cosine of 4 theta, 5 theta, any number as you like. All right. This gives you a quick way of finding those values, those identities. Any questions? So this is a side comment that this integer powers gives you this tool to find something new. Not new, but find something that we knew before in a different way. All right, any questions? All right. Well, maybe I should give you a break. Roots of complex number. Let's take a few minute break. Let's 5 minutes. I'm pouring a lot of new information into your brains. So,
Professor, can you leave that last slide up during the break?
sure.
Thank you.
So it's 12:10. Let's take a 5-minute break. We start at 12:15. I just let me. All right. So now we investigated powers of complex number. Now we're going to investigate roots of complex numbers. Let's say we want to find the nth root of z, which we call w. If w is the nth root of z and z is r cosine theta plus I sine theta, then we want to see what is w. We take w to be in polar form as the module of r and argument of phi. So we want to find r and phi. And then if we raise this equation to the nth power, then z will be w to the nth power. And w to the nth power is r to the n, cosine n phi, and sine n phi. So this r should be equal to r to the n. And then, so these two should be the same, right? And so r is r to the n, and therefore r is nth root of r. But then n phi should be equal to theta, but you know that we can add a multiple of 2 pi to the argument, and it will be the same number, the same complex number. Therefore, n phi is not only theta, is theta plus 2k pi. But in general, k can be any number. But you will see if you just for any value of n and theta, if you keep going different values of k, then these numbers repeat themselves. So if you solve for phi here, becomes theta over n plus 2k pi over n, right? So if k is 0, then you have theta over n. That's the first root. And then if k is 1, you can add 2 pi over n. And then you can add 4 pi over n and 6 pi over n and so forth. And then depending on what n is, if you have, for example, k is equal to n, you get 2 pi added to theta over n, which is the same as theta over n. And if k is n plus 1, it is the same as k being 1 and so forth. So then for this formula to work, k should be from 0 to n minus 1, because when k is n, it is the same as when k is 0. All right. So we have n distinct values here. Somebody's microphone is on. Please make sure that your microphones are muted. So we have this formula. So W, if it is n root of z, and z is r cosine theta plus I sine theta, then W has a module of n root of r and has argument of theta over n plus 2k pi over n. And n goes from 0 to n minus 1. All the other n's, all the other integer values of k just repeat themselves. So we have n distinct value for the nth root of z. So for k, we have n distinct w's for nth root of z. We call them wk for k equal to 0, 1, 2 to n minus 1. For example, w naught, w1, w2, and so forth. Therefore, the nth root of z is an n-valued function. All wk, which is nth root of z, are on a circle of radius nth root of r with angular separation of 2 pi over k. See this? You have 2 pi over n, it should be. All right, so because you have 2 pi over n and then 2 times 2 pi over n, and then this should be n, my apologies. So if you have, let's say, n is equal to 5, then the separation of these roots becomes 2 pi over 5. So we have 5 distinct values, right? So that needs to be changed. All 5 values of fifth root of I plus 1 are on a circle of radius. You see, let's say if z is I plus 1, it has a argument r of 1 squared plus 1 squared, so it's square root of 2. Then if you have the fifth root of square root of 2, you get, in fact, the 10th root of 2 as the argument, which is 1.072. That is the radius, that is the module, and they are separated by 2 pi over 5. And the first one is the argument of this, which is 45 degrees or pi over 4, divide by 5. All right, so we have pi over 4 divided by 5, which is pi over 20, and then plus 2k pi over 5, and k goes from 0 to 4. All right, if you show them on a coordinate system or complex plane, you see this is the first one when you have pi over 20, and then you add 2 pi over 5 to that, you get this point, and then 5 pi over 5, 4 pi over 5 is this one plus that, and then 6 pi over 5 and 8 pi over 5, and then 10 pi over 5 is 2 pi. You come back to the same point and then repeats. Okay, so that's why k goes only from 0 to 4. Okay, that makes sense. So all of these nth root of a complex number are on a circle of radius nth root of the module of the complex number, and they are separated by 2 pi over n. All right, any questions? All right, so let's put that up here, and then in particular, the nth root of 1 is very important and interesting. If omega is the nth root of 1 or omega k is the nth root of 1, k goes from 0 to k, 0 to n, then we have cosine of 2k pi and divide by n plus I sine of 2k pi over n. Because what? Because r for 1 is 1, so n root of 1 is just 1, so we don't have this, it's just 1. And theta is 0, so theta over n becomes 0. So we only have cosine of this 2k pi over n and sine of 2k pi over n, right? And all of these are on a circle of radius 1. So these are the nth root of 1, where k goes from 0 to n minus 1. And you see that omega k is equal to omega 1 to the power k. So omega 1 means when k is equal to 1, right? So we have 2 pi over n. And then omega 2, for example, is when k is 2. So it multiplies this argument 2 pi over n that by 2. So you see that omega 2 is omega 1 squared. Omega 3 is omega 1 cubed, and so forth. So omega k is omega 1 to the power k. And then the importance of these is that you can write this omega k in terms of this, sorry, we can write wk for any complex number as the first one of these, the omega naught, sorry, w naught times omega k, which is omega 1 to the power k. So if wk is the nth root of z, you can write it as omega naught, sorry, w naught, which is the first one of these when k is 0 for this, times omega k, which is this. If you multiply omega k by w1, you see that the arguments add, right? And the argument and the absolute values multiply. So you get that for any value. And then omega k can be written as omega 1 to the power k. So you can write it w naught times omega 1 to power k. So the importance of this is that you can write the nth root of w, the nth root of z as the first root of z, and then multiply by all of these that omega 1 and omega 1 squared, omega 1 cubed, and so forth until you repeat, right? Until you get all of them. And omega naught, as I said, is when k is 0, so it becomes like this. And if you see that here, nth root of k is third root of 1 is one of them is 1, one of them is here, one of them is here, and we call this omega, and this is omega squared, omega cubed. It will be the same as this omega naught. This omega naught for 1, if n is 3, you have k is 0, so we have cosine of 0 plus I sine of 0. So that's the 0th one, omega naught. And then omega 1 will be 2 pi over 3 cosine of 2 pi over 3 plus I sine of 2 pi over 3. That would be this point. And if you square that, you get this point. If you cube that, you get back to this point. And then another example is 4th root of 1. 4th root of 1, the first one is 1. The second one is I, and then I squared, I cubed, and 1. All right. And 5th root of 1 are it. So all of them has 1 in them, but then it becomes a what do you call this? This is pentagon, but it is multigon, right? becomes, if you have fourth power, it becomes a square, third power becomes triangle, and then becomes pentagon, and then becomes hexagon, and so forth. And all of them start from 1, and they are in the unit circle. All right. So these are the roots of a complex number that is in general like that. You can also write this in exponential form if you want, like nth root of r times e to the power of I times this, right? That's the general form. That is even simpler to write down. All right. Any questions?
I have a question. What is the difference between the W and the omega?
WK is the roots of Z, but omega k's are roots of 1,
Okay,
right?
thank you.
You're welcome. Any other questions? All right. So how do we define derivative of a function, and how do we define analytic functions? So that was 13.2. So 13.1 was generally the complex numbers in Cartesian coordinate or Cartesian form of complex numbers. 13.2 was the polar form of complex numbers or exponential form. And then we explored what you get if you multiply or divide or nth root and so forth. And in part 3, we're talking about complex functions. And before we go to some complex functions, because we need some definitions, we introduce some definitions here that we're going to need for later process. So I already mentioned unit circle. The unit circle is the circle of radius 1 centered at z equal to 0, the origin, and is given by the modulus of z equal to 1. This means that the radius is the distance of all the z values whose distance to the origin is 1, right? This is what this means. Absolute value of z equal to 1. So these are all points on the unit circle, and this is the unit circle. If this point is 1, all the points that have modulus 1 are in this, and they're denoted by this equation, and it's called the unit circle. What is the open circular disk of radius rho centered at z equal to a? Z equal to a is a complex number. If you have open circular disk around a with the radius rho. So we have this z minus a equal to rho. This circle is given by z minus a equal to rho, means that all the points in the complex plane that has a distance to a of rho. But this open circular disk is all the points that are inside this circle. Means the distance of them to a, see the absolute value of z minus a is the distance of the two numbers. The distance of all the z to a is less than rho. So that represents all the points that are inside the circle. And we call it an open circular disk of radius rho centered at z equal to a. Why do we call them open? We are going to define what we mean by an open set in complex plane later on, shortly. All right, so this is open circular disk. A closed circular disk of radius rho centered at z equal to a is given by the same thing but equal also in it. Means that all the points that are on the circle are also included in this set. So if these points, the circle is also in the set, we call it a closed circular disk. Why do we call it closed? We're going to define closed soon as well. An open circular disk that we defined here is also called the neighborhood of A of radius rho. And A has infinitely many of these neighborhoods, one for each value of rho. So rho can be anywhere between 0 to infinity. So each one of those can be a neighborhood around A. Of course, rho cannot be 0. If it is 0, it's just 1 point, but it can be any real number. A is a point of any of these neighborhoods by definition, because you see, if you z equal to A, if z equals to A minus A is 0, no absolute value of 0 is 0, and it is less than rho. So by definition, A is part of the neighborhood of A. All right, so these are some definitions. What is unit circle? What is circular disk? Open circular disk, closed circular disk, and so forth. All right, some more definition. What do we mean by point set? Point set is any collection of points in a complex plane, either finitely many or infinitely many points. So examples are solutions of a quadratic equation. In complex plane, solution of quadratic equation is always 2 points. So this first example has only 2 points. These points on a line has infinitely many points, but they are all on a line. And this one points inside the unit circle. This is also infinite number of points. But each one of these are point sets. Okay, depends on what we're talking about. All right, this is a set of points or point set. What is interior point of a set S? Interior point of a set S is a point of S that has a neighborhood consisting entirely of points that belong to S. You need to think about what it actually means. Interior point means, for example, let me write and draw some here to give you some example. Let me see. Yes, that's I plus 1 in the upper half plane. So if you consider all the points that are in the upper half plane, this complex number, plane, sorry. These are, this is the set point of all the numbers that are in the upper half plane. And 1 plus I is like this point. Is 1 and I. 1 plus I is this. So this is an interior point. Why is that interior point? Because there is a neighborhood around this that has all its points inside that set. A point of S that has a neighborhood consisting. So this is S, this is point, and it has a neighborhood of radius rho, right? All of the points in this neighborhood are points of this S. Because that is the case, this point 1 plus I is called the interior point of this S. Does it make sense? All right, so this is an example. Another one is the 0 in the unit disk absolute value of Z less than 1. Again, absolute value of Z less than 1 is the unit disk here. There are points that are inside this unit circle, and 0 is there. And any neighborhood of 0 that we take has all the points, not any neighborhood. There is one neighborhood, you see. It has a neighborhood consisting entirely of points that belong to S. So S is this unit disk, and 0 is there, and you have one neighborhood, at least, there are infinitely many, of course, neighborhoods of 0 that has all its points inside S. So S is the interior point of S. Any questions? These are some mathematical analysis definitions. So what is an open set? We said open disk before, which we call neighborhood. An open set is a set whose points are all interior points. Means that every point that is in the set is an interior point of the set. Means that for every point that you take, there's a neighborhood, no matter how small. There's a neighborhood that has all its points entirely inside there. For example, the open disk, open unit disk is like that. Any point that you take inside this, it has a neighborhood whose points are entirely in this. So all of its points are interior points.
I have a question.
All right. For example, this is this S is the set of S is the set of all let's say absolute value of Z less than 1. All right. But if you make if you consider another S, another set like P that is defined by absolute value of Z less than or equal to 1, means that the circle, unit circle, is part of it, then that doesn't have this property. There is a point that is on the in the set is on the circle, but doesn't have any neighbor, doesn't have any neighborhood whose all points are inside the set. Any neighborhood that you take, there are some points in it that are outside this S, this P. All right. So if it includes the circle, it is not an open set. It is a closed set. All right. As I said, examples of open set is the unit disk, absolute value of Z less than 1, or lower half plane, which is defined by Y less than 0. Right? This is all the points below the x-axis, but it doesn't include the x-axis itself. So every point that you take in that, it has a neighborhood whose all points are inside this set. So that this is an open set. All right, this is like S. Any questions? Is that clear? There are lots of definitions. We are squeezing a lot of information, new analysis information into one session. So it is a little bit confusing, I understand.
So for the neighborhood, we're just saying that there is at least one value of rho
Yeah, that's right.
that makes that condition true. That's where it's inside the set, right?
That's right. And,
Okay.
and if Y for Y less than 0, any point that you take that is below x-axis, no matter how close to the x-axis we are, we can take a neighborhood around it.
Because
right?
there's always points between
Yeah,
any point below the x-axis and the x-axis.
that's right.
Okay.
So this is called open set. Boundary point of a set S. Boundary points is a point whose every neighborhood contains both points that belong to S and points that do not belong to S. Like that circle that I said here, this point is the boundary point of this set or the disk. The points on the circle, if you consider all of the neighborhoods around them, has some points that are inside the set and some points that are outside the set. So that is that makes those points on the circle a boundary point for this set. All right. So that's that. And then the example, any real point X for the upper half plane Y greater than 0 is a boundary point. You see it again, this is the set, all the points in the upper half plane, and any point on the x-axis that you take, and any neighborhood of that has some points in the set and some points that are not in the set. Therefore, the points on the x-axis are the boundary points of this set. Make sense? All right. Again, points on the circle, unit circle, for the unit disk, argument of z less than 1 are boundary points. Okay, the circle is the boundary of the disk. All right, and the complement of a set. A closed set is a set that includes all its boundary points, and complement of a set of all points in the complex plane that do not belong to us. So if you have a set, the complement of the set is all the points in the complex plane that are not in the set. Like if you have an open disk, open unit circle, then all the points outside are the complements, and plus the circle. All right, and a set S is called connected if any two of its points can be joined by a chain of infinitely many straight line segments, all of whose points belong to S. And so that means that they are not separated. This is not connected because you go from here to here, you have to pass here, and some of these points are not in the set. This is not connected. But if they're connected, no matter what shape it has, then from any point to another, you can go in this way so that you just pass all the points that are inside the set. And a domain is any open and connected set, and a region is a set consisting of a domain plus perhaps some or all of its boundary points. So these are the definition so that we have. So I guess I stop here. I was hoping to cover complex functions, but it doesn't happen today. All right, so we're going to continue from here next time. All right?
All right, thank you, Professor.
Professor, thank you.
You're welcome.
Thank you.